I mean, this statement, the statement that this is equal to this is not true. Why? Do you know what? I mean, some of the statement is not true. Can you see why? Why this is not equal to this? Because the limit, because as you take the limit, t goes to infinity, this goes to 1, and this goes to 1. So the limit is not equal, because before you apply the L'Hopital's rule, you must make sure that the limit is either equal to both the limits must be either 0, or both the limits must be plus infinity or minus infinity, right? But in this case, you cannot apply the L'Hopital's rule. I think some of you made this mistake, and some other people said they wrote down some other people, when they wrote down their answer, they gave little details. When you write down the derivations, you need to give as much detail as possible, right? I mean, I don't expect one. I mean, at least 5 or 6 different lines would be good enough. Not writing like, for example, if you write something like the limit of 1 minus f tx is equal to the limit of 1 minus gtx. This is not good enough. There's no details at all. You have to, you're just writing the answer without giving any details, right? This is no details. I mean, if you write something like this in the exam, you will get no mark. Okay, so you have to explain how you got from this line to this line, right? And with you need to give as much detail as possible. Okay. So those are the 2 comments I have on the in-class test that took place last Tuesday. I assume all of you got the marks on the same day, right? All right. Any other questions you guys have? You want to ask me? No questions? Let me know, guys. If you have any questions, please let me know. All right. The next, okay. What I like to do today, I really want to finish things. Remember, last week I started. The final thing I did last Tuesday, you may recall, is this one. The final thing I did was to talk about this one here. I mean, semi-parametric estimation methods for VAR. This is the thing that I talked about last week, okay, before the in-class test. And the first method that I talked about, I will go over this again. The first method I talked about is known as the GEV method, right? The GEV method applies when the data set that you have looks like this, right? You have a series of data over a long period of time, and the extreme value that you are interested in is the largest point over that period of time. Okay? Okay, guys. So, you guys listen to me. So if Mn denotes the maximum, the largest observation, the CDF of Mn for n large enough can be approximated by this, right? And this, as you know, is known as the CDF of the GeV distribution. So now to find var, you set this equal to p and solve for x in terms of p, right? And you get this formula here. You get this formula for var. Now in this formula there are three parameters that we need to estimate: mu, sigma, and psi. Now what I told you last week is the following: is to estimate the psi parameter non-parametrically using one of these two estimators, and neither of these two estimators assume any distribution for data. So they are purely based on the order statistics. In other words, the data itself, right? They don't assume any distribution for the data. And okay, and then so estimate psi according to these two, one of the two estimators which are non-parametric, and estimate mu hat and sigma hat as the MLEs, right? So when I say MLEs, the method of MLE automatically assumes a distribution for the data. So the MLEs mu hat and sigma hat are parametric estimators, right? Whereas the estimator psi hat, as I mentioned here, the estimator psi hat is a non-parametric estimator because it doesn't assume anything about the distribution of the data. So hence, this estimator here for var is a semi-parametric estimator because it combines parametric and non-parametric estimators together to get an estimator for var. Right? Is that clear? Or was it clear to you last week? I mean, this is the last thing I talked about on Tuesday last week. So any questions on this you'd like to ask me? Yes? No? Please let me know, okay? So that's the first thing I talked about. The second thing which I want to talk about now is the following. And for that, I'm going to show you this picture here. You may remember this picture from a long time ago. That this picture here is used to, it's known as the definition 2 of extreme values, right? Whereas you draw a threshold u, this is known as u, the threshold. Right, this threshold is, and any data point that exceeds u is regarded as an extreme value, okay? And this is basically the definition 2 of extreme values. So under this, I'm going to write the following. So this is known as the number 2. Let me switch the pen. This is number 2. It's known as the GP method. GP stands for Generalized Pareto, as you may recall. Okay. The GP method, we assume the following, that is, Do you guys remember this equation? Do you guys remember this equation? We did this long time ago. This model is known as the generalized Pareto model. Do you remember or not? Come on, guys. Don't you remember this? We did this like way back in the beginning of the course. This is known as the generalized Pareto model, right? Okay. And U is the threshold. Now to find what we need to find is we need to find the var, right? So to find var, set g of x equal to p is the probability, and solve for x in terms of p. So this will become 1 minus q right, and you set this for you solve this for x in terms of p. So let me do it slowly in case I make mistakes. You know, I always make mistakes. So if you solve this, guys, you get 1 minus p divided by q to the power minus psi. So x will become mu plus sigma over psi. In brackets you have 1 minus p over q minus psi minus 1. So this is the expression for x in terms of p, right? So hence the var, the value at risk, is equal to mu plus sigma over psi divided by q. Okay, so this is the expression for var. Now the thing is we need to estimate var. So to estimate var, we need to estimate the 2 parameters here. Oh, sorry. It's not, it's u, not, this is u, alright, not mu. Don't confuse it. Do you have Tipex here, guys? This should be, this is u, not mu. Can you, any of you have Tipex here? No. No, do you? Sorry, sorry. I should have brought it. No, this one. I used it. I'm not familiar with this one. I will use the other one. Anyway, sorry. I mean, what I meant is, this should be u, not mu, okay? There's no mu in this parameter. Okay? Alright? No, I meant the other one. Sorry. Alright? There's no mu in this model because this should be u, okay? What I meant is this should be u, not this should be u, not mu. Cut down the okay. This should be u, okay. So the only parameters that we need to estimate, Right, we need to estimate two parameters in this case, which are sigma and psi, because oh man, because all the parameters are, u is not a parameter, u is a threshold, right? U is a threshold, it's not a parameter. It's u, all these are u, not mu. Okay, so we just need to estimate two parameters, sigma and psi. Alright, so, and as I said before, I'm going to estimate psi as one of the two parameters sorry, what did I do? Yes, should be ST. Are you okay, sir?
Yeah.
Alright, let me finish writing this, then I will talk. Alright guys, so did you follow what I said, guys? Any questions on this? So what I've done is to estimate the psi parameter, which is the shape parameter, using the same formulas I used. It's the same formulas I used in the GEV method, that is one of these formulas, right? And estimates the sigma parameter as the MLE. And as I said before, MLE assumes a distribution for the data, so it must be a parametric estimator, MLE. right? So in this equation here, you are combining two different estimators. One is a non-parametric estimator for psi and a parametric estimator for sigma, right? So therefore, this equation here, or this estimator here, is a semi-parametric estimator for y. Okay, guys? Any questions? Let me know, please. By the way, I did not say before, the k here is a number between 1 and n. N is the sample size, and k is any number between 1. I mean, there are methods for choosing optimal value for k, but that's beyond the scope of this course, so I will not discuss that. If you want to know how to choose k optimally, I can send you some papers on it. Okay. All right. The next thing I'm going to talk about is expected shortfall. So far, we talked only about VAR, or value at risk. Right. Now, I'm going to give you the proofs Do you remember the first property? What is the first property of expected shortfall? Do you remember what that is? What is it called? What is the name of the first property? Huh? Normalized property. And it says that the rho at 0 must be 0, right? But we know that var, we proved earlier that this is equal to 0, right? So this implies that the expected shortfall at 0, which is the integral of is equal to 1 over p times 0 to p of 0 times dt is equal to 0. So the normalized property is proved. Right, number 2. What is this property number 2? Can somebody read for me? Second property. Huh? Excuse me. What's the second property, guys? Huh? I can't hear you guys. Sorry, can you show it to me? You got it here or not? Translated. Translated property. Right, we know This is the translated property, right? Correct me if I'm wrong, because I don't have. So this implies that the expected shortfall at x is equal to 1 over p dt, right? And this is equal to 1 over p oh, what am I saying? Sorry, there should be a c here. There should be a c here. I left out a c. There should be a c inside. This is equal, there should be a c inside here. Okay, and this is equal to 1 over p plus c outside, and this is equal to es plus c. Okay. Okay, guys, did you follow this proof, guys, or no? Let me know if you are not able to follow this proof. Please let me know. There should be a c inside, guys. This is x. This is x plus c, and the same thing here. This is x plus c. Okay. Right. Okay, so that proves the second property. The third property, can somebody tell me what the third property is? I can't remember. I'm asking. Is the monotonicity, is that right? Is that right? The monotonicity, right? For the monotonicity property, we know that x less than y or x less than equal to y implies y this is the monotonicity property for y. So this implies that right, and this implies that and this implies right, so we have proved, right, we have proved that the monotonicity property holds for ES using the fact that it holds for var. We have proved that the monotonicity also holds for ES. Is this clear to you guys or not? Hello guys, talk to me. Yeah? Okay, please let me know if it's not clear. Okay, now the the next is the positive homogeneity property. That's number 4, right? For this property, we know that var at constant times x is equal to c times the var of x, right? We know this property. We proved this property last week or the week before, I can't remember, right? So this implies okay guys, now this implies, now if you divide both sides by p, okay, and finally, because of the definition, what you have here is the expected shortfall, and what you have here is c times the expected shortfall. Okay, so we have proved that the monotonicity property holds for expected shortfall. Okay, is that clear or no? Any questions, just feel free to ask, guys. So but by assuming that because a couple of weeks ago we proved that the monotonicity property holds for, not monotonicity, the homogeneity property holds for y. Now using that fact, we have shown that the homogeneity property also holds for dx, right? Okay, any questions, guys? You alright, guys? Let me know if you have any problems. You okay, my friend? You okay? Okay, good. Alright. Now, the next thing I want to talk about is estimation methods. Estimation method for, first I will talk about parametric estimation methods, and secondly I will talk about non-parametric, and thirdly I will talk about semi-parametric. Okay, so I will start with parametric estimation methods. Okay, So what A one, the normal distribution. Okay. We know from last week that for the normal distribution, the expected shortfall, the formula for that, you may recall, is the following. All right. Its MLA is mu hat plus sigma hat divided by P where mu hat is x bar and sigma hat is alright, this is the formula. Okay guys, and if you want to know how I got these estimators, you may want to look up in the, I sent you guys a link for the statistical methods course I taught 2 years ago. So if you haven't taken that course, you may want to look at the link about how to derive the MLAs for mu and sigma, right? Okay. All right. So that's one. Next one. Number 2 is the uniform distribution. Okay, this is normal distribution. Okay. Do you guys remember the formula for ES, for the uniform distribution? Is A plus P divided by 2 times B minus A. Alright, this is the formula for expected shortfall. We did this last week or the week before, I can't remember now. So its MLE is the estimator for A, the MLE for A, if you look at the link I sent to you guys, is the minimum. It's the minimum of x1 to xn. And the MLE for B is the maximum. Alright, so this is the estimator for expected shortfall if the data on the losses follow the uniform distribution, right? Okay. All right. Next one. That's number 2. Number 3. Number 3. The power function we know from last week or the week before last week, we know that the formula for expected shortfall for this is as follows. This is the formula for and its MLE is as follows. Sorry, there shouldn't be a hat here. I don't know why I put the hat. If you have a ink, can you ignore this hat, please? This MLE is as follows. So this is the MLE for. So this is the MLE for the expected shortfall. By the way, can you remove the hat in front of the ES? It shouldn't be there. This over here. Remove the hat. It shouldn't be there. I forgot to remove. Okay. The hat should be here. Okay. All right, guys. The next one. The next one is the number 4. Is the variable distribution, right? So suppose with CDF equal to okay. So this is the CDF for the variable distribution. Now we want to find the expected shortfall, right? You may remember from last week. Do you guys remember the formula for var last week? We did this last week. Come on, guys. This was the formula for var. Do you remember this? Yes or no? So to find the expected shortfall, what we need to do is to integrate this formula. So it will be we need to integrate this, and I'm going to make to do the integration, I'm going to make a substitution. So set I'm going to make the following substitution, right? So this implies that 1 minus t will be equal to EF minus y. So t will be equal to 1 minus EF minus y, and dt by dy is EF minus y. You guys following me or what? Hello guys, talk to me guys, please. I will bring you more chocolates if you talk to me. Alright, so I made this substitution, okay? Now under this substitution, let me put this here. You can see better maybe. under this substitution, what do you get? The integral will become, so the expected shortfall will become like this: theta divided by p. The limit at 0, when t equal to 0, this will be 0, right? And when t is p, it will be minus this. Okay, so we have inside the integral, you have y to the power 1 over beta and e of minus y dy. This is what you have. Right, now this guy here can be written, correct me if I'm wrong, I hope I am right. Okay, this guy here can be written as follows: right, where right, this is the definition. This is the definition of the upper incomplete gamma function. Okay, all right, so what I have used here, guys, hello guys, if you listen to me please. So what I have used here is in going from this, the first line, to the second line, I have used the definition of this function, which is known as the upper incomplete gamma function. Right? Okay? Okay? Alright. So that's this. Now we are not done yet. We are not done yet because we haven't found the estimators yet. So the guys, could you please listen to me, guys? So theta hat and beta hat are the solutions of the following equations. The same equations I wrote down last week, you may recall these. These are the same equations I wrote down. Right? So theta hat and beta hat are the solutions of these two equations, right? Where x bar is the sample mean and s squared is the sample variance. I mentioned that last week. If you want, I can write it again. Where x bar is the sample mean okay, and s squared is the sample variance. The sample variance always has n minus 1 in it, so not 1 over n minus 1. Right? So this completes the parametric methods. So just to summarize, just to recap, guys, I have talked about so far, I have talked about 4 different parametric methods for estimating ES. The first one was on normal distribution method, the second one on the uniform, the third on the power function, and the fourth is this one, which is the Weibull distribution. Right? Next one I will do after the break will be on non-parametric, how to estimate ES non-parametrically. Right? I will do that after 10 minutes break. Okay. So let's take a break, guys. I'm tired too. By the way, can you see this? Like, are these writing dark enough? Is it dark enough? Well, I can't see it. I can't see them just with my eye. Sometimes I can't see them, so I think they are not dark enough. Oh, no. Hello, how are you? Everything okay? Alright. You guys done your quiz? All of you done. You can hand it to me tomorrow if you want. Or if you've already done it, you can give it today. You've done it already. You're too fast. No. You done it, or you want to give it tomorrow? You can give it tomorrow. Are you done?
就是感觉好真的，我本来是想，他露出来更多，我想哦，就是多想一点。怎么回事？打不开了。不然想让它长度和可以长短，但是让它只长一点点，可能比较失望。它真的好长。腰买长买短。不冷，因为 来。对，然后我但我没敢吃药。
你这个人真包，为什么过节？
你去哪儿？昨天。刚刚啊。
我在回来这样稍微碰一下，从回来再出来碰一下啥？又抓到了，背着我出去逛皮。
不是为了
抓了现金。
主要是。
对。
再下一个什么？
那里边还有一个呢，现在就要做那个。别说了。不会写，我天！我看那个都看从哪开始写。
它的范围太广了，我不知道怎么写。对。它的范围有点。上了8周，不知道是哪周。我打针完了，我都没敢吃那种药。
打了啥针？
太弱智了，我没敢吃。我就只吃了那种中成药。对。
他们说打。
Normally, any topic you have, you should have a certain topic you like to work with.
特别深。
Oh, I can't see this one. You don't have.
就有经验在我那边。是个中国人。这好像是不是亚洲人？自驾好像是多少？
有自驾，GPP 免费的。不是上次打什么好像200多吗？ Here we go 。
就感觉挺酸的。我还能打流感疫苗。
我知道，我也能打。害怕。烧感又不会生病。
但我的英国是2天。
我也是。
但是还行吧。就跟普通感觉。
看见他那个针管，我就不太行。
可是他特别小。
你俩打是一个手工那个。
是吧？都是那个。这样。他那针管粗了一些点。这么细，然后这么感觉。那我没有。反正我觉得他扎挺深的。
这样能卖的贵一点。
自己扎的。
我觉得可能不敢戳那个细管，因为我觉得它像拔针。
还有一个针法，这个叫大龙招。就是还挺结实。
就是别人做好的，就把那指甲剪进去。
对。就是别人做的，在假针中。
我知道那个。
做完之后再卖给我。
我之前还看过张翰，他说感觉是老的。
基本上我就10个10的那种，就差不多。 你自己做，对。你要是自己做的话，怎么着得200？我没进。
你们12月还有计划？
好吧。
越来越长，越来越长。没有，全是我没有多好满，反正都是满的，我那时候是空的。我怕是。
有想法吗？
本来想买那个帽子，发现上边还有打折，这边不打折了。
哦。 这还没漏呢，没漏，这算什么？这有袜子，那也，这有袜子，袜子很那个，看不见我这。哇，好薄，而且这是黑的。哦，就是不用布的那种，不用打底数。对啊，而且我以为是底下全到一起。但我觉得太低了。这是厚的，这不薄。这样可以的。我先把肌肉投进去，然后他们不知道。对呀，这不是个学习曲吗？怎么就变成了？我们还有学习圈，我们还。
Hello guys. Is everybody back? Or is like one person? We are waiting for one person. Alright guys. Alright guys. Number 1. So I'm going to start talking about non-parametric estimators for ES. The first method is known as the historical method, and this is different from the historical method that we did for var. Remember, when we talked about var, we also talked about a historical method, and that one is different from this one, right? So suppose you have data on losses, say x1 to xn, right? And what you do is you order the data. you order the data from the smallest to the largest. So x, this is the smallest, this is the second smallest, and this is the largest. Okay, this is the smallest, and this is the largest data. Right? Then the historical estimator for expected shortfall is as follows: is 1 divided by n times p times the sum I from 1 to np of x I. And this is the, I mean, it's a very simple estimate. This formula here is the historical estimation for PS, right? Okay, where are you guys familiar with this notation? This notation here. You've seen this before or not? Integer part, yeah. So integer part of x, which means is the largest integer less than or equal to x, right? So for example, if you have the integer part of 6.1 is 6. Integer part of 5.9 is 5. Yeah? Integer part of 0.5 is 0, right? And so on. Okay? So that's it's the largest integer less than or equal to x, right? Okay, guys. So this is it's a very simple formula for estimating ES, right? So let's do an example, guys. Example 1. Suppose we have the following data. Say 9 minus 10 2 0 5 minus 5. Okay, 1 2 3 4 5 6 data points. So now the first thing, so these are data on losses, right? So the first thing you need to do is to arrange the data. So what's the smallest? Minus 10, minus 5, 0, 2, 5, 9. Okay. Suppose I want to find the expected shortfall at, say, 0.2. What would this be? If I want to estimate the expected shortfall at 0.2, what do you have? What formula do you need to use? It's used to 1 divided by n times p. What is n? N is what? N is 6. 6 times 0.2 is 1.2. So the integer part is 1. Okay, so So the answer is minus 10. Okay? You follow me? Now suppose you want to find the expected shortfall 0.9. Okay? So in this case, n times p would be 54, right? 5.4. So integer part is 5. So it's 1 divided by 5 times the sum I from 1 to 5 of this. So this will be equal to minus 10 minus 5 0 plus 2 plus 5 divided by 5. Okay, so it will be, is that right? Yeah. So it will be minus 8 divided by 5. So that will be your expected shortfall. Okay. Is that right, guys? Yeah. Okay. So that's the historical method is a very simple method to estimate OR as well as ES, expected shortfall. Yeah. That's number one. Number two, so suppose you have, this is the same bootstrap method I talked about last week. Suppose you have data on losses. Say x1 to xn. The method works like this. The first thing is, the first thing you do is the following. You compute the empirical CDF, which is just this. I mean, I talked about this last week, you may recall. And the second step is to simulate b is an integer, right? I mean, for both these steps, there are programs in R. I'm sure all of you know the R software. There are programs in R for doing the first step and the second step, right? Okay. And the next step use the historical method to estimate ES Okay, so you have B samples. You have B samples, and you estimate ES for each of the B samples by using the historical method, right? So resulting in so this will be the estimate of ES for the first sample, and this will be the estimate for ES for the second sample, and so on up to you have B samples. So this is for the B sample. Okay, and the final step you estimate the final estimate for ES as the mean or the median of these. So in other words, is either the mean Alright. Okay, guys. So this is known as the bootstrap method for estimating ES. It's very similar to the bootstrap method for VAR. Alright. The only difference is that we are estimating ES, not VAR. Okay. Alright. Okay. Next method. You can guess what it is. Number 3. Any questions on this, guys? Hello, guys. Any questions on this? Yes, no? Let me know if you have any questions. Feel free to ask me, guys. Number 3 is the jackknife method. Alright, so once again you have data on losses. Okay, the first step Alright. Right. The second step keep doing this until the very final step, which will be the following. Use right, and finally you guys okay? Any questions, feel free to ask me, guys. So okay, all right, guys. So is this clear to you, all of you guys, what I did here? So what I've done is similar to the jackknife method I talked about earlier. All right, at every step you remove one data point. In the first step, you remove the first data point and estimate ES using the historical method. In the second step, you remove the second data point and estimate ES using the historical method. Until the very final step, you remove the last observation in the data and estimate it using historical method. Right? So you have these n different estimates, right? Okay. So the final estimate is taken as the mean or the median of the n different estimates, right? Okay, guys. Is that clear, guys? Any questions? Okay. The next one. Okay. So this is jackknife method. Next one I'm going to talk about is number 4. Number 4 is the kernel method. Kernel is different from the kernel method I talked about before. Okay. The kernel method works like this. So suppose you have data on losses, say x1 to xn. Okay, these are data on losses. The kernel estimate for ES is defined, it's a complicated expression. Well, it's not as complicated as you think it is, but it is relatively complicated to what you've seen before. So if you could give me a few minutes, I will write it down. The kernel estimate for ES is as follows. Just bear with me, guys. Just bear with me, right? Okay, just keep use this H. H is this. A this, and I know it's as I said, it's a little bit complicated, but I'm not going to ask you this in the exam though, so don't worry. Okay. And finally H is the bandwidth. So this big expression here, when you see it, right, this the first line gives the estimator for, gives the kernel estimator for expected shortfall, right? And all these are, so Q hat is given by this, AH is given by this, A is given by this, KH is given by this, and K is the kernel. The kernel is usually chosen to be, I think I mentioned this last week, the kernel is usually chosen to be the PDF of the standard normal, which is this one. I'm sure all of you know this. This is the PDF of the standard normal distribution, right? And H is the bandwidth. So when I say bandwidth, it controls how smooth the kernel estimate is. If H is small, then it will be zigzaggy, right? It will not be smooth. If H is large, it will be more smoother, right? So it controls the smoothness of the kernel estimator. And one of my students, I mean, from years ago, did a project on expected shortfall, and he found that the kernel estimate is one of the best among all the estimators for ES. The kernel estimate is one of the best estimators, right? Anyway. Okay. Any questions so far, guys? The next one will bring you memories, because this is the next one is actually. You've been to the room next door. The G209. This is G207, right? G209. There's a picture of somebody on front of that. Can you remember who that is? I'm sure you pass that place every day. There is a picture. When you go to G209, there's a picture of somebody on the front door. Do you know who that is? No? Come on, guys. You don't know? Have you ever checked? I mean, when you go to, okay, let me go and check now. There's a picture of somebody outside. This room here, not G209, G207. This is G207, right? What's the picture of the guy in front of this room? Do you remember the name? Come on, guys. I'm in this room here, G207. There's a guy there's a picture of somebody in front of this room. Who's that? Huh? Come on, guys. You want to check? Go and check. Go and check now. Go and check now. Just go and check now. Just you see the picture that you have on this door is Professor Richardson. It's the picture of him. Didn't you see that or not? All this time we've been coming to this room for many times. Anyway, guys. So this method, the number 5, is named after him because he was a professor at Manchester a long time ago. Obviously. So it's named after him, right? So it's called Richardson method. Suppose you have data on losses, right? So the first step is to compute f hat. which is the empirical CDF. The empirical CDF effect. Second step, simulate right. I mean, as I said a few minutes ago, there are programs in R for doing this, for computing the empirical CDF, and also for simulating a random sample from FF. Here n is different. This is capital N. It's different from little n is the sample size. Capital N can be anything. It can be 1,000, million, whatever number. Okay, so you shouldn't confuse. They're not the same, right? Okay. Right. Number 5. Come on, guys. Are you okay, guys? All right. Are you with me so far? Right. Here in step number 5, we are computing. We are repeating step. Sorry, we are repeating step 2 and step 3 1,000 times. Right. Okay. We are repeating step 2 and step 3 1,000 times. So after 1,000 times, you get 1,000 different estimates for ES. And what you're doing in step 5, is take the average of them, right? Okay. So let me say where. Okay. All right, guys. That's step 5. Next one. We're getting there almost. Number 6. Step number 6. this is step number 6. So what I'm doing here is to, you see what I did over here. I computed Mn as the average of these 1000 estimates. Okay. Now I'm defining Sj as the values of M and J for k plus 1 different values of this. And so N1 could be like 1000, N2 could be 2000, N3 could be say 5000, and so on. Right? So you choose these values and compute the corresponding this and call it Sj. And the final step, this is the final step. This is going to take a while for me to write down. So let me, just bear with me. Don't, I can make a lot of stupid mistakes. This is going to take me a while. It's gonna take me a while, but I don't just so one. Just be patient, guys. Don't let me do some stupid mistakes. I don't normally do a lot of mistakes. Do you know what I have written? This is the final step to your relief. Right, this step is the final step, which gives you the final estimate for expected shortfall, and is defined as this divided by this. I mean, what is this here? This is what? This is a determinant of a matrix. I'm sure all of you know determinant, right? And this is determinant of another matrix, right? So that's the final step of the Richardson methods. Now we are done. Before you leave, just make sure that you see the photo of Richardson before you. It's just outside this door. I will see you guys tomorrow at usual time, 4 o'clock. Okay. And I will try to mark this before that. If you have any questions, just see me around. No. You done? You're cooked now. I can shoot. Okay. It's all right.
Should I live here?
Yeah.
Yeah, thank you.
Thank you. Richardson. This name is outside. It's called Richardson method. Richardson's method. This photo is outside the door. You should take a picture.
Okay.
Yeah.